Hi class, so we're picking up today with our continuing discussion about enthalpy and thermodynamics starting on page 30. So enthalpy values for chemical reactions have been tabulated under the standard state, a commonly set of conditions indicated by a delta H naught with a little circle in the superscript. Constant pressure is considered 1 atmosphere. Enthalpy is not defined under constant temperature. Temperature, however, is usually considered to be 298 Kelvin, which is 25 degrees Celsius, about room temperature, unless otherwise noted. So here's how we may use some enthalpy values. So how much heat is produced by the combustion of ethylene by 0.538 grams of oxygen? So here we have the chemical reaction of ethylene, C2H2, reacting with 5/2 equivalents of oxygen gas to form 2 equivalents of carbon dioxide gas and liquid water. So the delta H naught for that equation under standard conditions is negative 1,301.2 kilojoules. So if that is sort of describing the amount of enthalpy or heat energy that's being released per mole or per 5/2 mole or per 2 mole of this reaction, we can then figure out under specific circumstances how much heat is being released. So in this case, we're questioning, well, how much heat is released if we had about 1/2 gram of oxygen? So we first need to convert that into moles of oxygen. So we take grams of oxygen divided by the molecular weight, gives us 0.0168 moles of oxygen. We then calculate how much energy is released by that many moles of oxygen, and we can take the negative 1,301.2 kilojoules per 5/2 moles of oxygen. Because remember, this enthalpy value is per coefficient, essentially, of the reaction. And so you got to divide by 5/2 moles, and that ends up giving us a value of negative 8.54 kilojoules of heat energy are released when about 1/2 gram of oxygen is reacted with ethylene. The standard enthalpy of formation, the delta HF naught, is an enthalpy change for the reaction in which exactly 1 mole of a substance is formed from free elements in their stable state under different conditions. So, for example, we can look at the standard enthalpy change for the oxidation of carbon. Here we have carbon solid reacting with oxygen gas to form carbon monoxide gas and 1/2 an equivalent of oxygen gas. And the enthalpy of formation of that would be listed as negative 111 kilojoules. We can consider a sort of a hidden per mole implied per mole off to the side. So I always read these standard formation with the dot as being negative kilojoules per mole with an implied per mole. The heat of formation of individual components of the reaction can be used to determine an unknown step using Hess's law, which we'll use. The enthalpy change of the process equals the sum of the change in the various steps. Hess's law is useful because some reactions are difficult, if not impossible, to investigate and make accurate measurements of experimentally. So we're going to use the standard heat of formations of some values to calculate the enthalpy change for the combustion of methanol. So here we have the combustion of methanol, which is 2 equivalents of methanol liquid reacting with 3 equivalents of oxygen gas to form 2 equivalents of carbon dioxide gas, 4 equivalents of liquid water, and an unknown heat of change for the overall reaction. So using an appendix and values that you would be provided, we would have delta HF naught for each of these components. It's negative 239.2 for methanol, 0 for oxygen, negative 393.5 for carbon dioxide, and negative 285.8. And remember, the units for all of these are kilojoules per mole. Now we can discover what the delta H is for this entire reaction by considering all of its components. We would take the sum of the number of moles times the heat of formation of each product, minus the number of moles times the heat of formation of each of the reactants. So here's how we calculate that for the products. The delta HF for the products is going to be equal 2 moles times the heat of, or rather 2 moles over here for carbon dioxide. So 2 moles of carbon dioxide times the heat of formation of carbon dioxide plus 4 moles times the heat of formation of water. That's going to be equal to 2 moles times negative 393.5 kilojoules per mole, and our moles cancel. plus 4 moles times negative 285.8 kilojoules per mole, and our moles cancel. We can then calculate that the delta HF for the products is negative 787 plus negative 1143, giving us an overall heat of formation of our products of negative 1,930 kilojoules. We then do the same analysis for the reactants, where we have our delta H for the reactants is going to be equal to 2 moles times methanol plus the heat of formation, or 2 moles times the heat of formation of methanol plus 3 moles times the heat of formation of oxygen. So that would be 2 moles times negative 239.2 kilojoules per mole, and the moles cancel, plus 3 moles times 0 kilojoules per mole, and that whole term goes to 0. And we would discover that the heat of formation of our reactants is negative 478.4 kilojoules. Now that we have our heat of formation of all of our products and a heat of formation of all of our reactants, we can figure out what the delta H is for the whole reaction by setting delta H equal to products minus reactants. So our products would be negative 1,930 kilojoules that we calculated minus negative 478.4 kilojoules, giving an overall delta H for this entire reaction as being negative 1,451.6 kilojoules. And now on to a few additional topics about thermodynamics, and as we are going to be applying them to equilibrium chemistry. So thermodynamics is the study of thermal, electrical, chemical, and mechanical forms of energy, and thermodynamics is important to how energy changes during a chemical reaction. What we've been talking about so far has been strictly the heat energy of the reaction. So delta H, when that's positive, heat is going into the reaction and it's endothermic. When delta H is negative, it's exothermic and heat is being released by the reaction. And of course, we've seen this before, but it's very, very important that when we have a reaction like hydrogen gas and half an equivalent of oxygen gas forming water, and we have a delta H associated with this reaction, we know that this minus sign tells us that it's exothermic and heat is being produced by the reaction, so you can write heat as a product. This is all incredibly important, which is why we've gone over it so many times, and the heat is going to be placed on the right side of the reaction, considering it a product. This is important to chemists because we can then control the reaction by heating or cooling, depending on which side of the reaction we want to favor, but more on that a little bit later. The next step is to talk more about how spontaneous a reaction is going to be, because thermodynamics can actually be used to tell us whether or not a reaction will or will not happen. In order to do that, we have to understand enthalpy, which we have a pretty good grasp of by now, and next we need to consider entropy. That's given with the symbol delta S. The more formal definition is that it is unavailable energy, but we can consider it as disorder. So here's a few examples to really understand how disorder is represented. So how does the entropy change in the following processes? So when you freeze liquid water to form ice, randomness is decreasing in that situation. We have something like liquid water that is flowing all over the place, and we're forming a three-dimensional, very structured, ordered solid, ice. So if randomness is decreasing, that must mean that disorder is decreasing, because we're going from something that's not organized to something that is highly organized. So delta S is going to be negative. It's going to be less than 0 in that situation. Subliming dry ice. That's a situation where we go from solid carbon dioxide, which is dry ice, and it sublimes to form gaseous carbon dioxide. In that situation, we're going from something that's structured and ordered to something that's very unstructured and disordered. So in that situation, subliming dry ice is going through a phase change where disorder is increasing. So delta S is going to be positive. It is going to be greater than 0. If we had a gas that we heated from 60 to 80 Celsius, disorder is increasing there. The pressure is going up and the particles are moving around a lot faster and creating more chaos. So we have delta S is greater than 0 for that. If we were to condense water vapor, we're going from gaseous water down to liquid water. So we are creating something that's more ordered, so disorder is decreasing. So delta S is a negative. And now for an important one. We're increasing the amount of matter. We have moles of our product is greater than our moles of our reactants. This is a situation where we are simply reacting things to make more things. In that situation, disorder is increasing. If we have one reactant and we form 5 products as it decomposes, that's an increase in disorder. So that's a delta S is greater than 0. Next, we're going to talk about Gibbs free energy. Now, Gibbs free energy is described as the relationship between enthalpy and entropy of a system. Gibbs free energy is not something that you can readily measure. It's not a physical property that's hanging out in the world. It is always relative to enthalpy, temperature, and entropy. And these are measurable quantities. So you can measure these quantities and immediately calculate the delta G. So delta G is considered the spontaneity of the reaction, and it's described with this equation. Delta G naught is equal to delta H naught minus T delta S, where delta H is our enthalpy. It is either going to be endothermic or exothermic. And T is our temperature, which is going to be in Kelvin, and that's always going to be positive. Also, we have entropy, S. That's positive or negative. Is disorder increasing or is disorder decreasing? The sign of delta G tells you whether a chemical reaction is thermodynamically favorable or not. So we have a couple of columns here, but we're going to rewrite our equation. So we have delta G is equal to delta H minus T delta S. In one situation, we have delta H is exothermic. We are releasing heat energy as the reaction happens. In this situation, we have an increase in disorder. Delta S is increasing. So we have heat energy being released, disorder is increasing. These are two very favorable situations for a chemical reaction. So it's exothermic and entropy is increasing. In that situation, we have a negative value and we are subtracting a positive value. If T is always positive because it's in Kelvin, that means that in this situation, delta G is always negative. If you have a negative value and you subtract an overall positive term, this whole thing over here is a negative, so we always end up with a negative value here. In that situation, we have a delta G is less than 0, and we call that exergonic, being negative. So free energy is being released. So we have the same prefix as for exothermic. In this situation, we have a delta G is negative. That is a favorable reaction and it will happen spontaneously. On the other side, we could have a situation where we have a delta H that's plus, that's positive, that's endothermic, and we are creating a more ordered system. If disorder is decreasing, so if delta S is negative, then we are decreasing disordered, which is another way of saying we are increasing ordered. So if you consider a situation where you are flooding a system with heat energy, you are putting heat into the system, and somehow that's creating something that's more ordered, that's never going to be spontaneous because that's very difficult to impossible to do. So you have delta G is a positive term minus a negative term that will always give you a positive value. In that situation, delta G is greater than 0. We call that endergonic. A reaction is unfavorable and not spontaneous. And now a quick note about units and substances for the problem sets. So I'm going to use problem number 2 as an example. So problem number 2 is unique, I think, to this problem set in that it has a lot of different ways to do it. So in the answer key, what you'll see online is one way to do problem 2. What I've done here is write out a few different ways. So problem 2 can be done by figuring out the potassium nitrate solubility, and it's described in terms of a volume of 100 grams of water. You can then calculate the mass of potassium nitrate that you need, which is 140 grams. You can then figure out how many moles. You can take that 100 grams of water, convert it then to liters of water, and then calculate the molarity of potassium nitrate, which is what the question's asking for, and you get something like 13.5 molarity once you get moles per liter. This is one way of doing it where you figure everything out individually and piece it together. The other way is you can actually take this whole problem and piece it together, and once you cancel all your units, what you're left with is just moles per liter. There's more than one way to do a problem, but what I'm going to be looking for now on, which I think problem 2 is a really good example of, is that you need to keep your units and substance organized and actually display them every single time. Because when we communicate science, you have to include the number, the unit, and the substance every single time. In medicine, if you were to say that you need 50 of something, nobody's going to know what you're talking about. You have to say 50 cc's of morphine. Or if you're making something in the lab, you need 5 grams of potassium nitrate. So in word problems, you must always use the number, the unit, and the substance, because you are all going to find ways of answering these problem set problems and exam problems that are different than the way that I did it. And there's always going to be more than one way to correctly solve a problem. And you need to be successfully communicating your science so that I can read it and understand it and see that the route to your answer makes sense. So from now on, please make sure that you are always doing unit and substance for every number that you write, so that you can make sure that everything makes sense. And otherwise, I will be sending out an email with more detailed information about the exam tomorrow on Tuesday, and have a nice rest of your week.